Just to recollect what we have seen so far, we are seeing about frequency response analysis, which is needed to check for the stability of a closed loop system. The simplest closed loop stability analysis based on Routh criteria, which expects a polynomial equation. Of course, the polynomial is written for the denominator of the closed loop transfer function. Otherwise, by writing this closed loop, or simply by equating the denominator of the closed loop transfer function to 0 and writing that polynomial in terms of this Routh array, we can say about the stability. But this method is not suitable for system with dead time, but this dead time systems are many so common in chemical engineering. So we are going for the other method, which is based on frequency response analysis, which is Bode stability criteria. This Bode stability criteria is based on this amplitude ratio and phase angle of this what is it? Open loop transfer functions frequency. For the open loop transfer function, we'll simply vary the input frequency, and we'll be finding this amplitude ratio and the corresponding phase angle. This amplitude ratio and corresponding phase angle will be plotted in log and semi-log plots. Okay, and corresponding to the crossover frequency. The crossover frequency is 1, for which phase angle is equal to -180. Otherwise, corresponding to the crossover frequency, if the amplitude ratio of the system is higher than 1, then we say it is unstable. That is what is called as the Bode stability criteria. But still, this Bode plot is also, or this Bode criteria is also failing for some of the systems. Otherwise, we have discussed. No? Yeah. Whenever the trend of this amplitude ratio versus omega is having not a monotonous trend, otherwise the amplitude ratio is high going and again coming down. For such systems, we cannot make use of for such kind of amplitude ratio versus omega plot, we cannot make use of Bode stability. So still there is another method, what is called as Nyquist stability, but Nyquist stability criteria is very elaborate, and we cannot have a rigorous discussion for that. To simply say, this Nyquist plot is simply the another variant of this Bode plot. Instead of plotting that in log and semi-log plot, this is plotted in a polar plot, which is again it is about again the effect of increase in omega. So starting from 0 to starting with 0 omega, we will increase omega up to plus infinity, and we'll mark this AR and phi variations. So AR is nothing but the distance from the center point, what is called as this radius of the this circular it is simply the radius of the locus of this Bode plot. This what is it? Nyquist plot is simply the locus of amplitude ratio and phi in the polar plot, and the distance from the center point, the locus points, how far it is away from the center point is given by that is equal to the amplitude ratio, and the angle it is making with the center point, angle it is making with the the horizontal axis called as a phase angle. Otherwise, I will again write it, better write it. People can join till we are making this review of the past classes. So I'm going to use my board. Better before that, let me share the screen. Yeah, share screen and whiteboard. Yeah, there is some chart message available. Let me check what is it is. Repeat on why do we need frequency domain analysis in place of Laplace domain? Frequency to say the need for this frequency response service, the need is because of always the simplest stability check is route stability, but route stability is not suitable for systems with the dead time. But dead time systems are very common in chemical engineering. So otherwise, to handle this kind of dead time systems, we need to go for this in a study, which is this Bodek stability. One நிமிஷம். Oh, there are many screens. ஒரு நிமிஷம், ரெண்டு screen வருது. Yeah. Let me use a whiteboard. Whiteboard என்ன பண்ண போறோம்? We are going to see about this Nyquist plot. Okay, Nyquist plot எல்லாம் நிறைய கொஸ்டின்லாம் கேட்க முடியாதுப்பா எக்ஸாம்ல. Only will restrict to Bodek plot. It is simple idea about Nyquist plot is needed. Yeah, Nyquist plot is a polar plot. Polar plot என்னது சர்க்கிளா இருக்கும். Okay, நல்ல சர்க்கிள் போட்டுக்கலாம். These are all coming as ellipse. Okay, center point வந்துருக்கணும். Okay, so this another one more question is there. We can't use Laplace domain for dead time system. Yeah, dead time system வந்து e power minus tau ds வரும்லப்பா. E power minus tau ds you want to write in polynomial. This still we are using Laplace transform தான் யூஸ் பண்ணிட்டு இருக்கோம். Laplace transformல this frequency instead of step input, no, step input was used for the stability checking. Now we are using frequency input. Okay, Matheswaran. Okay. This dead time system we can approximate with polynomial, but that is still only approximate. Instead, this Bode plot is very rigorous and much useful for the stability studies. Okay, idhula pathina Bode plot is simply AR versus omega. This killer plot clear pannira. I will just write how this Bode plot will look like and how the yeah, now fine. So this is AR versus omega in terms of logarithmic. So that means we'll be having 0.01, 0.1, 1, 10. The Mari we have this logarithmic values for the logarithmic values for amplitude ratio. Likewise, for omega also we have in logarithmic coordinates. So this is your 0.11 and 10, 100 like this. And we'll make this, we can easily plot in this AR and omega by simply having this low frequency and high frequency asymptotic values. For a first order system, say normally this is till the value of tau omega equal to 1. We have this horizontal line. After then, it is having a slope of -1. Otherwise, slope is -1. Okay. This is the Bode plot for first order system. Of course, how does that? The other plot, the another plot is phi versus omega. Okay, so phi and omega. Phi starting from 0, -0. So this is say somewhere around -90 and -180, and we will have maximum of say 360. So normally phase lag, so always minus only. And for the case of first order system, we have maximum phase lag is -90, corresponding to omega tending to infinity. So the midpoint always corresponding to omega of 1. Here we'll be having a phase lag of -45. So maybe I'll use another color. Oh, sorry, nala trend. So you can this will be this kind of plot like this. This is phi versus omega, but this phi versus omega normally we won't use this asymptotic. We have to actually calculate the points and mark. Okay. We need not calculate for we can simply mark for the 0 and the point, this midpoint and the last point. Last point is obvious -90, midpoint is obvious -45, and starting point is 0. So the 3 point மட்டும் தெரிஞ்சா போதும். Normally we'll make much use of this amplitude ratio plot than this phi plot. Okay. And coming to the 1 minute pa. Yeah. What do you want? Sorry for the disturbance. Okay, in the car. Yeah, this what is it? Nyquist plot. Nyquist plot looks like Nyquist plot is what is it? Polar plot. Yeah. So polar plot will be having circles. No, circle போட்டிருக்கோம். Okay. Yeah, nice circles. And we'll be marking this. Sorry. Variation of omega again, the same way as like polar, as like Bode plot. Starting from say this. Let us take this is center point, and this corresponds to say 0.5. This is your 1, and this corresponds to say 2, like that. And corresponding to your omega of 0, we have AR equal to 1 for the case of first order system, and it will go up to AR of 0, right? Yeah. So how does that varies for increasing values of omega that is plotted? Okay. So this is where this is a Bode plot. This is a Nyquist plot for first order system. Of course, you can mark the direction also. So it's starting from 0 to infinity. 0 to infinity. Omega is equal to 0 to infinity. The same way you can also plot for the reverse one, which is 0 to minus infinity. So that will be the dash line. I'll tell you upon now. From here it will go. This is your for 0 to infinity, and for 0 to minus infinity, if you mark, it will go like this. Actually, everything is within the 90 degree. So you have the mirror image. I could not draw it correctly, which is 0 to minus infinity. So the Nyquist stability criterion is based on the concept. What is it? Always we can mark this unit circle plot, which is having a radius of say 1. And if the Nyquist plot of your system, open loop transfer function, is encircling this unit circle, otherwise if you have this kind of Nyquist plot, then your system is said to be unstable. Otherwise, it won't be most of the time simply a circle. It will be spiraling circle or something like that. Otherwise, say suppose you have this kind of starting point somewhere here, அப்படியே இங்க இருந்து ஆரம்பிச்சு அப்படியே போயிட்டு உள்ள வரும். அந்த Nyquist plot புக்கில் பார்த்துக்கோங்க. I cannot easily draw that. அந்த மாதிரி டயக்ராம் பண்ணுற அளவுக்கு I don't have a software learning. If at all needed, I have to simply copy that. Of course, I had shown one such thing in the last class. 1 minute, I will check it again. That is, we are referring to Nyquist plot. ஒரே ஒரு plot பண்ணி காமிச்சிடுறேன். Sorry. Yeah. So this is a Nyquist plot representation for the first order system. Okay. So this is how the polar plot will look like. So you can mark the amplitude ratio and phase angle. Amplitude ratio for the starting point is 1, and the phase angle for the starting point is 0. Amplitude ratio for the ending point is 0. Otherwise, in the limit of omega tending to 0, you will be getting amplitude ratio equal to 0. The corresponding phase angle is minus 90. The phase angle is the angle it is making with a horizontal line. At the starting point, horizontal line angle is 0, and at the ending point, which is omega tending to infinity, you have the angle of minus 90. So this minus 90, and for the case of second order system, எப்படி இருக்கும்னா maybe I can show you only the arrows. So it will go like this and it will end this way. And for third order system, it will end at the third quadrant, which means 3 into minus 90. So 270 degree. Yeah. Likewise, fourth order system, or otherwise with increase in order of system, we'll be having this Nyquist plot to even encircle this encircle the origin. Okay. And I have tried to given this give you the Nyquist plot for one example I have given. I will refer to my book. Okay. We are just reviewing what we have seen so far. No, today's class, there is, I'm just giving an example for a Nyquist plot. How does it look like? Yeah, right. So this is an example for this system K power it's a first order plus dead time system for which starting from omega equal to 0 and omega up to infinity, or is last making some angle with the axis. Okay, this is actually in terms of Nyquist stability. Actually, this for the given system corresponding to some value of k, say value of k equal to 1.9, actually the system is found to be stable. Otherwise, this, if you combine this, what is it, omega equal to 0 to infinity and omega equal to 0 to minus infinity to 0, otherwise this total Nyquist plot is not encircling this -1. Otherwise, the -1 should be lying within this the rendu boundary. The curve, if it is falling within, then the system is unstable. So there is such example here. Say this is shown with a different scale. Don't simply compare this. Of course, the scale of this diagram A and B are different. Here the -1, there is unit circle is of this diameter, and the system is actually k into e power minus 0.5 s divided by s plus 1 with a value of k equal to 5. For that, the Nyquist plot is coming around this unit circle. So otherwise it is an unstable system. Otherwise, to say about the stability with Nyquist diagram, you should compare with this unit circle. Okay, that's our point. Of course, it is said to be that this Nyquist plot is much more better than even Bode plot. Maybe wherever the Bode plot is failing, we can still use Nyquist plot. If period treatment and all, we can always rigorous treatment and all we cannot easily give, which will which is also not needed. Okay, let us not worry about that. And going to today's class, which is about advanced control schemes. Okay, so far we are seeing about only one kind of simplest controller, which is feedback controller. Take a measurement and compare with a set point and give the output to the controller, and the controller will manipulate the input. Okay, input to a process. Now we are having a different sort of control schemes. Say for okay, this is the simplest control already we have seen. So what we are this is about feedback control of a dryer. Otherwise, how do we? Otherwise, there is a drying process happening. There is a wet material available, which has to be dried by blowing air, and by measuring the air temperature, we are controlling. We are saying about the dryness. So, if the exit air is say coming at a temperature higher than the this temperature of water vapor, or is temperature of the saturation temperature of the water vapor, say corresponding to 1 atmosphere, the saturation temperature is say 100 degrees Celsius, 100 oda jaasti air temperature vandichina, then it indicates that all the moisture is removed. Okay, otherwise we don't have any moisture left out. Otherwise, it is a kind of ensuring that all the moisture is taken in the air. So simply by measuring the air temperature, we are controlling the drying process, and this measurement is taken, and accordingly we are adjusting the steam flow. So it's the simplest feedback controller. There is a measurement, there is a controller, and the manipulator variable. Manipulator variable is nothing but the steam flows. By adjusting the steam flow, we can increase the temperature of the air entering to the process. And let us see how to implement the another way of control, what is called as we are going to control with another mode. Instead of taking only one measurement, let us take one more measurement. See, we can take a measurement of the air temperature, air entering to the dryer, and this TT refers to temperature transmitter. Okay, this TT refers to temperature transmitter. This is TC, temperature controller. So this temperature of the air is measured, incoming air is measured, and that is going to the temperature controller. To the temperature controller, the set point is given by the another controller. So there are two measurements and two controllers, but only one manipulator variable. So the manipulator variable is still the steam input. Instead of taking only one measurement, we are taking another measurement. In what way this is helpful? So otherwise, for the measurement variable, otherwise, வர்ற ஏரோட டெம்பரேச்சரை மெஷர் பண்ணி if you try to control the this drying conditions, it will be there will be a lag. Otherwise, this entire material has to be otherwise the air has to pass through the entire material and it has to leave, and the leaving temperature is measured, and again we are controlling the temperature. So instead we can simply measure the air entry temperature. Air entry temperature, if it is lower, immediately you can increase the steam flow. If it is higher, and we can reduce it accordingly. So otherwise, in addition to a single, otherwise in place of a single measurement, we have two measurements and also two controllers. But there is only one. What is called as, the inner loop is called as the secondary loop. The master loop, there is a overall loop. I will before going to that, I will also explain with another way of another is the same kind of control for controlling the tank temperature. So there is a tank, there is a water inflow and water outflow. We want to control the temperature of the tank contents. So we can measure the tank temperature, say tank temperature or the outlet temperature, obviously the same, and give it, and that measurement will be given to the controller. This controller will adjust the control, this what is it, final control valve. That will adjust the steam opening. Now, in addition to this measurement of tank temperature, we can also measure the steam temperature, and the steam temperature is measured, and accordingly steam inflow is adjusted. So otherwise, only one manipulation, but there are two measurements and two controllers. Of course, the set point is given to the primary controller or the master controller, and the set point for the inner controller is actually given by the this what is it, the primary controller. We can represent that in terms of this block diagram. So there is a process, and we take a inner. There is an inner loop and outer loop. This inner loop is the there is a measurement, and it is given to the comparator, for which the set point is given by the first controller, the first or the primary controller. So there are two measurements. This is only an approximate diagram, or is the better diagram is given here. So normally we'll be having only one loop. Now there is an inner loop. So in the inner loop, there is a measure. We are taking the value. There is the measurement. This measurement is given to the comparator. The set point for the secondary controller is given by primary controller. Still only one control valve. There is a final control element. So எதுக்காக இந்த மாதிரி system is needed? Say suppose you have a system that measurement is taking a long time, so you will have a slow control. Instead, you can take a simplest measurement and accordingly adjust the manipulation. Say otherwise, this is a simplest way of measurement. No, we can measure the inlet air temperature, whereas outlet air temperature will be delayed. No, this air has to pass through this drying this materials. Whatever the time needed, no, there is actually delaying. It is giving a delayed measurement. Normally, the inner loop will be a faster loop. So, a very fast action will be taken, and which will uh, enhance the overall control. Okay. So for example, here there are 3 measurements taken and 3 controllers available, but only 1 manipulation. So what is the ultimate objective? Ultimate objective is to what is it? We want to control the reactor contents. To control the reactor contents, what we will do, we will measure the temperature of the reactor contents, and we will adjust the this what is it, coolant flow. Okay. There is ultimate. We will have this manipulation is jacket flow, and measurement or the final objective is to objective is the temperature of the reactor contents. So we are measuring the reactor contents, and instead of directly this is going given to the controller, final control element, there are other 2 loops available here. The another loop is the measuring the jacket temperature, and it is going to the another controller, what is called as TC2. This TC1 is the master controller, which is the reactor temperature controller, and this inner one is the jacket temperature controller. And still there is another inner one, what is called as the flow. We can measure the flow of this jacket fluid and accordingly adjust the valve opening. So otherwise there are 3 loops here. The master loop is the temperature controller 1, and inner loop is TC2, and inside inner there is another flow control. So normally the flow control will be used in the inner control, because flow measurements are quite faster, and also the dynamics of this flow system, which is the time constant of flow system is simply volume by volumetric flow rate. Say volume of this line, volume of this pipe segment, and volumetric flow rate. There is again very fast. So the time constant of this process, which is nothing but the flow process, is very fast in comparison to this temperature system process. Temperature process is how does the jacket temperature affect the reactor contents. Likewise, how does the reactor content temperature affects the TC1 is about the temperature control. This is jacket controller. Yeah. How does the final objective is to control the tank temperature, control the reactor temperature. You can measure the temperature, or measure the jacket temperature, or measure the flow of jacket fluid. But the final objective is temperature control. So we can have these other 2 controls also. So this is the innermost loop, which will actually minimize any fluctuation in the flow. Otherwise, we are simply measuring the flow, and accordingly the valve opening is adjusted. The another thing is the jacket temperature will also affect the process. So we can measure the jacket temperature and accordingly increase or decrease the opening. And the final thing is the major loop. There is the temperature. According to the temperature, we can increase or decrease the opening. So otherwise, in the cascade system, we need to have 1 manipulation and 2 or more measurements and controllers. Okay. We'll again go through this here. So we, in the case of this dryer system, we are adjusting the steam flow. So normally the final control element is simply a control valve. Okay. Otherwise, we are adjusting a flow. Here, we are adjusting the flow based on the measurement of temperature and settings to the controller. So controller, we have this set point, and there is a process variable coming. So according to the difference, the error is going to the final control element, and error is given to the controller, and there is a manipulation value reaching this final control element, and it is adjusted. Okay, in addition to TT1 alone, we have 1 more temperature measurement and 1 more controller. But for this inner controller, actually this is inner loop. For this inner controller, the set point is given by the master controller. So master or primary, or inner or secondary, or even slave controller. Okay. Only this kind of qualitative treatment will be given for this cascade control. maybe the base பண்ணி problem கேட்கணும்னா என்ன பண்ணலாம்னா you can ask we'll be asking you to reduce the block diagram and obtain the overall closed loop transfer function. அதுக்கு ஒரு சின்ன எக்ஸாம்பிள் I will give you. எத்தனை பேர் இருக்கீங்கன்னு பார்த்துக்கலாமா? 35 people 36 students are available. Good. Okay, we'll just again give the main points. The first controller, essentially called as the primary or master controller, gives orders to the secondary controller. Okay, there is a secondary controller set point is given by the first controller, primary controller, and the purpose of cascade control is to achieve greater stability of the primary process variable by regulating secondary process variable in accordance with the needs of okay. And an essential requirement for a cascade control is the secondary process variable should be fastly responding. So otherwise, normally this flow processes are very fast processes. How do we say it is flow process? For the flow process, you can still model them as first order system with the time constant of what is it? Volume by volumetric flow. Volume of the system. There is in the case of a pipeline measurement, volume of the pipeline divided by the volumetric flow, which will be very less in comparison to in the case of a thermal system. So for thermal system, what is the time constant? It is again say mcp by h into a. It will be coming, no? So for the case of again natural convection process, there will be again more resistance. So that such process and all will be taking a long time to respond, whereas the flow process will be responding faster. So we can adjust the inner loop. Otherwise, the overall control action will be much better with cascade. Normally, the cascade control will be used in most of the chemical engineering systems. Say, okay, this is one of the example. For this cascade control, you are asked to find the transfer function y by x. Okay, as Gunala, I will see the theoretical aspects. So the normal feedback control is simply take a measurement and give it to the controller, and there is a final control, and it is affecting the process. Okay. And this cascade control is there are two measurements and two controller and only one final control limit. So the inner measurement, no, in this inner loop will be normally for the fast loop. So otherwise, the inner loop will be most of the time a flow loop. Say for example, the level system, we want to control the level of this by increasing or decreasing the opening of the pump output. Okay, valve output. So we have this level setting, and level data is taken, and level it is compared with in the level comparator. Okay, this level controller, and this it is opening and closings are happening. Whereas we can implement this cascade system with another flow measurement. So the flow measurement is going to the flow controller. So to the flow controller, the set point we are not giving. The set point is given by the level controller's output. So the overall response will be actually faster with cascade control, provided the inner loop is a faster one. Okay, inner loop faster, outer loop or inner loop faster. So the normal inner loop measurement is normally flow. Of course, in this case, no, in the first case, we actually have inner loop is also a temperature measurement and temperature controller. But in comparison to the outer loop, you can definitely say that inner loop will be faster because you have a limited capacity. Capacity of this system. No, this is the system for this TT1B. Whereas for the 1A, the overall process will be material passing through the entire dryer contents. Whereas this is only measuring the air temperature. No? Air temperature within this area, within this conical shape and the bottom line. We are measuring the air temperature. According to the air temperature, we are increasing or decreasing the steam opening. So otherwise, the inner loop should be a faster loop. Okay. அதுக்கேற்ற மாதிரி இந்த ஒரு ப்ராப்ளம் பார்க்கலாம் இல்லையா? See, for example, here the inner loop process is having a transfer function of 1 by 2s plus 1, whereas the outer loop is having a transfer function of 1 by 5s plus 1, or Kp by 5s plus 1. Of course, you can say that inner loop is having a time constant of 2 and outer loop is having a time constant of 5. So definitely this inner loop is faster. Of course, in the inner loop, the measurement is also having a transfer function, or this measurement is also having a lag, first order lag. Of course, overall, if you see the process, how if you don't have the, you can simply compare this is coming because of the cascade. If you don't have that, this total thing you can remove and you can simply replace with a unity transfer function. Okay, you can of course check and compare with this cascade normal feedback இருந்துச்சுனா எப்படி இருக்குங்கிறது ஒரு சின்ன calculation போட்டு பாத்தீங்கன்னா you can see that if you have the inner loop to be of faster loop, then the overall response is actually better than the normal feedback. Okay, இந்த ப்ராப்ளத்தை நீங்க ட்ரை பண்ணி பாருங்க. So I will tell you how to solve this problem. You consider the inner loop. For that you obtain the closed loop transfer function and have that as a single block. Then now you consider the total loop. Okay, this problem already I have solved it. It's available in my one of the book, but nothing to worry. This inner loop alone now consider. Say you have x and y. For that you have this feedback loop. It kind of transfer function you can obtain. What is a closed loop transfer function, and have that as a single block, and now have this total loop, which is another 1, 2, 3 elements will be there. Okay, and ஒரு சின்ன நல்ல ப்ராப்ளம் I will take an example which is நமக்கு பழைய கேட்ல கேட்ட क्वेश्चन ஒரே ஒரு क्वेश्चन காமிக்கிறேன். கொஞ்சம் நீங்களே யோசிக்கலாம் இல்லையா, அதுக்கான क्वेश्चन I am giving. Yeah, say now the question is how many loops are there. So the measurement, actually we want to measure the we want to keep the concentration of the reactor at constant by making a concentration measurement and giving to a concentration controller. CC refers to concentration control. So the set point is given to the concentration controller. So how many loops are there? யாராவது question பார்த்து சொல்றீங்களாப்பா? Diagram is given. So there are many controllers. C refers to controller, TC1 temperature controller and TC2 temperature controller based on the jacket temperature. FC refers to the flow controller. Of course, the final control element is simply this control valve. This I by B refers to there is a response available. Good. 5 loop irukappa, check பண்ணுங்களேன். 5 இருக்காதல. Always one loop consists of one controller. One measurement and one controller corresponds to one loop. No? The overall loop is C measurement. There are 3 inner loops. 1, 2, 3 inner loops. This I by P refers to current to pneumatic. The controller output is actually a current signal, whereas for the control valve we want a pneumatic signal. So I by P refers to this current to pneumatic converter, or what is called as transducer or converter, I2P converter, current to pneumatic converter. So there are 4 loops. Originally we want to measure concentration and keep the concentration at control by increasing or decreasing the jacket fluid. Okay, but in between we have this measurement of temperature and measurement of reactor temperature, measurement of jacket temperature, and also measurement of the coolant flow. Okay, so flow controller, jacket temperature controller, and reactor temperature controller. The outer is the concentration controller. Question. So what is the control strategy given, and what is the primary control variable? Can we match now without referring to this? So what is the control strategy? Control strategy is definitely a cascade control. So what is the primary control variable here? Maybe you can type also in the chat box. What is the primary control variable? already சொல்லியாச்சு still primary control and yeah, there is a response. Good. Concentration. Nice. So let's see that. What is the slowest controller? So which is the slowest controller here? அடுத்த கொஸ்டின் என்னென்ன ஆப்ஷன்ஸ் இருக்கு? ஸ்லோயஸ்ட் கண்ட்ரோலர் இஸ் slowest controller will be again actually the concentration controller. Yeah, the primary control variable is concentration, and the slowest controller is actually concentration controller. Because the concentration normally, how do you measure a concentration? Measure the concentration. So in the case of this automated system, we'll be measuring using this GC or HPLC or whatever. Yeah, normally these systems are used. This instrumentations and all normally takes time after about minutes, few minutes. Whereas the time constant of the other processor normally after seconds. So otherwise the concentration controller is the slowest controller. So what is the fastest controller? So normally the fastest controller will be the innermost control, innermost loop. So normally the flow is the innermost controller, and otherwise the flow is the fastest process. And the flow process is having this transfer function as flow process is having the time constant as what is it? Volume by volumetric flow rate. Volume by volumetric flow rate of this pipeline segment. The pipeline what is the volume of the pipe, volume of the fluid contents divided by volumetric flow rate. So there is a very fast or which will have very low value of time constant. Okay, the rendu mark ketta question idu. We can read out this concentration cascade controller has one manipulator variable and more than one measurement. Here the manipulator variable is control valve opening. The measurements are concentration, temperature of the reactor contents. Okay, and the primary control variable is concentration of the reactor. Slowest controller is the concentration controller, and the fastest is the flow controller. The output of the flow. Okay. Okay, இதே மாதிரி இன்னொரு ப்ராடக்ட் ஒர்க் அவுட் பண்ணலாமா? ஒரு நிமிஷம். Let me see. Let me look for some more questions. I have one such question here. One minute. Yeah. Here I can. Yeah, already solved it. This is having 3 loops. So the thing is, we want to control the temperature of the reactor contents. That is happening by temperature controller 1, temperature controller 2, and flow controller. Okay. Okay. To summarize, in the cascade control system, we'll be having one manipulator variable, and of course there is only one output variable of importance. So the we'll be making 2 or many measurements and 2 or many controls. Whereas the inner loop controller settings are given by the outer loops controller. Okay, for example, for the TC1, the output is given by CC, and for the TC2, the controller setting is given by TC1, and for the innermost, the next outer level controller is giving the set point. Okay. So only qualitative questions can be asked. Maybe if at all any problem is to be asked, maybe the mari oru chinna block diagram kodutittu you may be asked to find the overall response. So for that you can start from the innermost loop solve pannittu then outer come to the outer loop. So adukapra outer loop. Okay, that way you work out. And now we are going to the another way of control, what is called as feed forward control. So iduvare paathathu ellame feedback control. Even the cascade control is also a feedback control. In the case of a feed forward control, okay, this is giving the schematic here. So there is a process, and we take the measurement of the process, and we adjust the inflow. We adjust the inflow or outflow. That is, we adjust the we manipulate the this flow to the process, flow or what is it, settings to the process. So otherwise we don't measure the disturbance. So any kind of disturbance can enter the process, but only by measuring the process output, there is a input going to the controller. The measurement is going to the controller and it's compared to the set point, and there is a manipulation reaching the process. Now, suppose you have a good measurement of the disturbance, all the disturbance entering a process, then you need not measure the process output. According to the measurement of the disturbance itself, we can adjust the manipulation. Okay, adjust this valve opening or closing. So otherwise, this feed forward requires you to have a good measurement of all the disturbances entering the process. Otherwise, this is like என்ன சொல்லலாம் அந்த in the case of say the risk by okay, I cannot give you example, nice example. Okay, so this feed forward control requires you to have a good measurement of all the disturbances entering the process, and how does the disturbance affect the process. Otherwise, we should know the relation between the disturbance and the process. What is the connection between this disturbance and process? We should have the proper model equations. Whereas here, in the case of feedback control, we do not need any model about the disturbance. There is connection between the disturbance and process. We need not have any such relation. Whereas what we are doing, simply measure the output and adjust the flow. Any amount of disturbance can enter, and the disturbance effects will be reduced simply by measuring the output alone. But here, this for the disturbance to affect the process, and accordingly you take the corrective action, will be actually there will be a delay, because the disturbance is entering and it will take its own time to affect the process, and only after it affecting the only after it affects the process only you will take the corrective action. Whereas here, even before it is affecting the process, or even before the disturbance is affecting the process, you are taking the measurement of that, and you know the connection between this disturbance value, how does the disturbance will affect the process, that you know. Otherwise, you know the perfect model of the perfect relation between D and P, disturbance process. Only if you have such a good relation, you can implement this feed forward controller. Okay. So we don't have any, there is no feed forward here. There is no feedback. So there is a measurement is going, the information is going to the controller, and so there is a feedback, there is a recycle, information is given back. Here you don't recycle anything. There is no information recycle. So you know, how does the D affect the Y? There is already known. There is only for some simpler system, whereas for which you know the relation between D and process can be controlled with feed forward. So normally we'll have a combination of that feed forward and feedback. That will come to that shortly. So let us see the feed forward implemented for controlling the reactor temperature. So for the controlling the reactor temperature, of course, you can measure the flow to the reactor and accordingly adjust the coolant temperature. So otherwise, we don't take the measurement of the reactor temperature. We know how does the we know the relation between the feed and the reactor temperature. So if you increase the feed, reactor temperature will drop, or if you reduce the feed, reactor temperature will rise. So you know that qualitative relationship. Not only the qualitative, the exact relationship is known. Accordingly, you are increasing or decreasing the jacket fluid temperature. So this is a feed forward control strategy. Okay. And you can have this combination, feed forward and feedback. How to have that? There is you make the measurement of the feed reactor temperature. So there is a temperature transmitter that is going to the temperature controller. So to the temperature controller, again there is additional information coming from the this flow transmitter and flow controller. So the combined effect is now given to the manipulation. So it is a combination of feed forward and feedback. Otherwise, this combined strategy is always better. Otherwise, this feed forward alone requires you to have a very good model of the relation between the disturbance and the process. If you don't have such a very good model equation, then always go for this feedback and feed forward. So always feedback will eliminate always feedback is, of course, it's a slow control system. Say if you have a first order system with a control, again it is going to be a second order, but this feed forward, there is no such increase of order. No, you are taking the measurement and accordingly increasing or decreasing the flow. So otherwise, if the flow transmission or flow measurement process is a first order, only the first order relation is there still to the final control element. Whereas with feedback service, if you don't have this feed forward, if you have this feedback alone, the measurement, if it is having a first order information, first order lag, and again adding to the controller, again the overall response will be slower in comparison to the feed forward. Okay, this is the block diagram representation. Say you have this originally, this is the thing. Now, so the disturbance will normally enter to the process. We don't have the measurement of the disturbance in the case of original feedback, whereas in the case of feed forward, we know the measurement of, we have the measurement of disturbance, and how does it affect the process, that thing is known. Accordingly, we have this, otherwise we are computing this feed forward computation, otherwise how much is the controller action to be given, that and all calculated based on the relation between the process and disturbance, and accordingly we have this total effect is now acting on the control valve. Okay, based on your chinna problem paakalam, then you'll be in a position to understand better. 1 minute. Another about 2-3 minutes only. Okay. A very simple problem is available. At least this problem will help you to understand how this controller is there. How does the controller feed forward controller is implemented or calculated. That are I can get to know. Yeah, 1 minute. Fine. So we have a process and a disturbance. Okay. And process transfer function is available and disturbance transfer function is available. So the disturbance variable is entering, and we are calculating this GF. GF is actually the transfer function. That output will actually act on the final control element. Okay. See, for example, okay, let us read the problem. The transfer function of the process is, say, first order process, and the transfer function, disturbance transfer function, there is also which is a second order relation. How does the disturbance affect the process is given by a second order relation. And what is the perfect transfer function for the feed forward controller, so that you don't see any variation in the output. Say there is a disturbance entering. In spite of any disturbance, the YS should remain constant. That is the objective. So this disturbance is affecting this process in this way, GD, which is a second order relation. The original process is phi by S plus 1. Okay, say the Y of S you can write. How do you write this Y of S? Which is equal to ds into GDS, one summation, plus there is ds into GDS. This is one. The another group is ds GFS and GPS. Okay, both are added here. No. Okay. So there is a transfer function of the, there is a relation between YS and DS that we are writing. For any amount of DS, YS should not vary. Okay, what is the meaning of this perfect controller? The YS should remain. There should be no deviation in the output for any changes in disturbance. So YS we want to keep it as 0 for any value of DS. So that means you are making this left hand side to 0. So this thing to be, otherwise we need to find the value of this group. Of course, d of s is not 0. So d of s is the error, what is a disturbance variable. So otherwise we want to find what is this value. Otherwise, ultimately we are going to find this gf, which is nothing but the feed forward transfer function that is estimated, that is acting on the final control element. Okay. So this gf, okay, is the gfs should be equal to what is it, minus gds by gps. So if you have this feed forward transfer function, or this is referring to the block diagram, or this is nothing but the feed forward computation. So we have the disturbance measurement, or disturbance process ku ana idu relation koduthachu, disturbance measurement, and or this feed forward computation, and adoda value is equal to gd by gp, minus gd by gp. So minus plus and all depends on these two groups. Okay, here both are added to the output depends on gp plus gd. Suppose you have gp minus gd or something like that, then accordingly you write this in the proper way. Maybe sometime it may be plus or minus mati kuda varala. Say for example, one more such problem is available here. So for this the gc or gf, nothing but the gc or gf is gd by gp. இங்க பாத்தீங்கன்னா gd minus gd by gp ன்னு போட்டுக்கோம், இங்க plus gd by gp ன்னு போட்டுக்கோம். Reason is, okay, normally you will be having a positive and it will be a negative. So ரெண்டுமே பாசிட்டிவா இருந்துச்சுன்னா இங்க மேல நெகட்டிவ் வரும். ஓகே, அதாவது these are all simply algebraic relations, no need to worry. Okay, to quickly summarize, in today's class we have seen about the qualitative aspects of cascade control, and followed by we discussed about feed forward control. So for the feed forward control, we need to have a good measurement of the disturbance, all the disturbance variables. Normally in any system we cannot measure all the disturbances entering. So for example, in the case of a temperature of a reactor contents, so you have to measure the ambient temperature and even the ambient temperature variation, jacket temperature, and even the feed entering temperature and feed flow rate. But normally we'll measure only the say feed temperature alone or the reactor temperature alone. We don't have the measurement of all the process variables affecting the process. In such a case, you can simply implement the closed loop, the feedback control. If you have a good measurement of all the process variables affecting the process, you can implement feed forward controller. So the overall objective is to keep the output to be constant, or the Laplace transform of output should be 0. Okay. Okay, இதோட the advanced control strategy, only a qualitative aspect is given, but that much is enough for our final examination. Even the normal class நடத்தினா கூட இவ்வளவு நடத்துவோம் நம்ம. In the next class, we'll see about the controller strategies for distillation column and heat exchangers. இதுக்கான qualitative treatment will be given. இன்னொரு கிளாஸ்ல அதுக்கப்புறம் டெஸ்ட் வந்துடும். டெஸ்ட்டுக்கு அப்புறம் ஒரே ஒரு கிளாஸ் will have, so that we'll see the overall output of the class. No, இது வரைக்கும் என்ன படிச்சிருக்கோம், what is the objective of the class, whether did we cover every aspect, overall என்ன புரிஞ்சது, இதெல்லாம் வந்து ஒரு கிளாஸ்ல லாஸ்ட் கிளாஸ்ல பார்த்துடலாம். So 2 more classes will be there. The one will be before the test, one after the test. Okay.